So this video is going to be the only video for this week, and it covers a topic called polar coordinates, which is actually probably going to feel very simple for most of you because we've actually already done this in some way, shape, or form. And so here is kind of the general overview of what this section covers, right? So everything in this class has been devoted entirely to understanding the unit circle and understanding angles and triangles and sines and cosines and all of these trig values and stuff like that. And so hopefully we have kind of realized that there is a usefulness. There's a usefulness in being able to work with circles and angles and stuff, and we've been able to extrapolate a whole bunch of information from doing so. And so what polar coordinates focuses on is really this kind of relationship between the x, y variables and the r theta variables. So polar coordinates focus on, like I just said, the relationship between this x, y set of variables and what we call the r and theta variables, right? And hopefully we have seen that pretty much the most useful parameterization for a circle, and let's say this is, say, a circle of like radius 2, per the videos from last week, a nice parameterization of this circle is simply x is equal to 2 cosine of theta, or t if we were using t, and then y is equal to 2 sine of theta as well. And this is a circle that starts right there when t is equal to 0. It goes all the way around like so. It ends up back here when, theta is equal to 2 pi, right? Nothing super spectacular to it. And there's plenty of other little parameterizations we could have used, right? It is totally okay if we had said, done something like cosine of 2 theta and sine of 2 theta. That would have worked as well, except to get all the way around the circle now, hopefully we remember that the period of a graph like this would only take pi amount of time to get all the way back around the circle instead of 2 pi. So we already worked with this notion of letting x equal something in terms of theta and y equal something in terms of theta. And so polar coordinates is the very general relationship. It is the very general relationship between x, y, and r theta. And the relationship is as follows. So we call this set of coordinates here, we call these polar coordinates. Okay, and if you've ever looked at a map before or a map of the world or things like that, you have likely seen what's called a polar grid. And a polar grid looks something like this. So I'll try and draw it for us. So there's one. No, it's not going to make it. Let's make another one. Okay, let's make it over here. There we go. There's 2, right? Let's try and make these kind of the same size around. Let's make a third one. So here's going to be the third one, right? And so polar grid kind of looks something like this. And it's where our coordinate system has been split up into a bunch of little pieces. And usually they're pieces that have to do with the fact that we are going in some sort of circular path. So usually it kind of looks something like this. I guess I could have done the other one all the way around like so. Right, this is what a polar graph looks like. But polar coordinates focus primarily on this set of r and theta. And so the relationship that we should already know for x and y is, well, it's this relationship. It's the relationship that x is equal to r cosine theta, and y is equal to r sine theta. Okay, now what does this mean? Well, we've already worked on this. So for instance, if we were talking about a circle of radius 2, we used to just pop in an r equals 2 over here, so on and so forth. But the way that you can think of polar coordinates is it's just another system where we can graph things. And guess what kind of shapes it graphs really, really well. Over here in polar coordinate land, I'm gonna call this space over here polar coordinate land. Okay, in polar coordinate land, it graphs things like circles really well, because we already know that if we stay over here in XY land, to graph something like this, it's like x squared plus y squared, equals 4. And on the other side, to graph a circle of radius 2, in polar coordinates, it just ends up being r is equal to 2. And in fact, it ends up just being this particular circle right there, right? That one right there is a circle of r is equal to 2, right? R is equal to 2. So to graph the same exact circle over in polar coordinates, it's a much nicer equation, r equals 2. And we talked about kind of where this comes from, but let's kind of go over it one more time. Actually, before I go over it, maybe I'll just kind of introduce how we graph things in polar coordinates, just to kind of make things so that you know how to get around. So if I want to plot a point in polar coordinates, say the point 2, pi over 4. Okay, the way that it works is we always start from the origin. That's what we call our pole. And we start graphing this point from there. And we say, okay, I'm going to go out a radius of 2, and we're going to be located at the angle pi over 4. And so pi over 4 would be right here, and the radius of 2 is exactly on the blue circle. So that point in polar coordinates is the point 2, pi over 4. Now, what is that point over in regular, what we might call rectangular coordinates, rectangular or Cartesian coordinates? What is this point? Well, we know this is a point root 2 over 2, root 2 over 2. Okay, so how do we get there? Well, from this bit of information, right? From this bit of information, we can figure out what our theta is, right? We know that our theta is going to be pi over 4, right? And then we can figure out, this isn't going to be the point root 2 over 2. This is going to be the point just root 2 and root 2. Why is it the point just root 2, root 2? Because we're on a circle of radius 2, so everything has been stretched out. Apologies. And we could use that point to figure out root 2. If we didn't know what the hypotenuse was, we could very quickly use the Pythagorean theorem and figure out that this missing side is going to be just 2. Okay, so we can kind of work back and forth a little bit of algebra to figure out that point. So let's plot another one. Let's see, another point that we could plot on a polar graph might be like -2, pi over 4. Now, where does that point go, right? What does it mean to have a radius that's negative? Well, we go out to pi over 4, and we go out to where positive 2 would be, except then, because it's negative, the negative indicates that we're actually just going to flip over to the other side. And so this point right here is the polar point -2, pi over 4. Now, if you're, thinking very critically, you could have also described this same point as having radius 2 and being all the way at whatever this angle is. And so I believe that's going to be the angle 5 pi over 4. So both of these points describe the same exact place in kind of a polar graph, okay? And so before we kind of continue, just the purpose of working with polar coordinates and the purpose of learning this kind of transformation is that when you start dealing with circles next quarter and you start taking a calculus class and you start realizing you have to do a bunch of calculus dealing with circles, it turns out that doing calculus on stuff like this is kind of a pain in the butt. But doing calculus on something that's as simple looking as r equals 2, right, if you do it over in polar coordinate land, ends up being really nice. And so sometimes it makes sense for us to use this polar coordinate transformation and go from our rectangular coordinates in terms of x's and y's and turn things into polar coordinates. And we've already been using kind of a version of polar coordinates in this class. We've just been letting x equal cosine of theta and y equal to sine of theta. Right, so we already have like a slight taste of this. It hasn't been too bad so far. And so let's see. So where else can we go with this? So from this, it might make sense to just try and show you, how do you write something that's in Cartesian form, in rectangular form, into polar coordinates form? So, for example, and this is going to cover, going from rectangular coordinates, right? This rectangular coordinate system that we know and we love, from rectangular coordinates all the way to polar coordinates. All right. So, for example, what we're going to do is we're going to write the Cartesian equation, write x squared plus y squared equals 9 in polar form. Okay, now this is a circle of radius 3. Hopefully we can kind of take an educated guess as to what this is going to look like. But if you don't know, right, the way that we approach this is we're starting our journey in x and y land. X squared plus y squared equals 9. And in order for us to get to polar land, right, we need to take our little boat, what we call a transformation, and our transformation is x is equal to r cosine theta, and y is equal to r sine theta. And so all we're going to do, when we say that we're changing variables, all we're doing, just like we've done before, is we're just simply going to plug in these values for our x and y and see what it looks like, right? It would be the same thing as changing currency. If you were going from one country to another, they give you a conversion factor. Whatever we get in this country is still going to be the same as what we had in the country we started with. It's just going to look a little bit different. That's the only thing that's going on. So when I plug these in, this transformation, into my x and my y, I'm going to get r cosine of theta squared plus r sine of theta squared equals 9. So again, that's like we're starting to leave our Cartesian land, or our x and y land. Now we're going to, just kind of factor some stuff in, distribute in this exponent because it's just one term. So cosine squared theta plus r squared sine squared theta is equal to 9. That's not so bad. And we're kind of still moseying along our little way. We're kind of getting closer now, though. So I can factor, say, an r squared out of everything, and I'm left with a cosine squared theta plus sine squared theta, and that equals 9. And hopefully, if we paid attention in my last video, we saw that we have a trig identity here. We have one of the nicest trig identities. It turns out that sine squared plus cosine squared is always equal to 1. And so this equation, as we start to get even closer to our polar land, if we kind of head up here, my little arrow kind of looks silly. Let's do that. We get just the equation r squared equals 9. And this becomes in polar land, this is just the equation r is equal to 3. Now, you could do r is equal to -3 because if you draw a circle with radius 3, right, hopefully you saw when we graphed polar coordinates, all it did was it just flipped it from one side to the other. So you're just going to get a perfectly symmetric circle anyways. But this equation r equals 3, how do we graph this in polar land? Well, in polar land, what this says is that we're going to draw a circle of radius 3, right? Well, what angle do we put in? Well, there is no angle restriction. And the theta can be anything that we want here. And so we're just going to put in some shape that has a radius of 3 all the time for any angle of theta. And so this right here is the equation r equals 3. That's it, sketched nice and easy, no problem. That is the equation in polar coordinates. Now, what if this question had us going backwards, right? What if the question had said, write r equals 3 in Cartesian coordinates. Okay. Now this one is a little bit more challenging. Okay. It's a slight bit more challenging to do because to go backwards here, we don't exactly have a transformation. I mean, we know this. We know x is equal to r cosine theta, but how does that help us know that I'm supposed to end up at x squared plus y squared equals 9? And it doesn't. And so what we are going to do here is we're going to very cleverly make an observation. And one observation that we're going to make is that in general, the equation of a circle is x squared plus y squared is equal to r squared. Okay, so we know that x is equal to r cosine theta, y is equal to r sine theta, but we also know that in general, x squared plus y squared is equal to r squared. And what does that mean? Well, that means that if we had, say, cosine squared theta plus sine squared theta, that's supposed to equal 1, right? Right, that right there is supposed to equal 1. And if I multiply everything by r squared, so I'm going to multiply that r squared, that by r squared, and this by r squared, we get this really interesting thing that happens. What happens here, right? What is this? Well, that is just r cosine theta squared. The other one is r sine theta squared, and on the right side we have r squared. Well, r cosine theta, that's the same thing as x. R sine theta is the same thing as y, and r is still just r, right? So we get this really nice, this is where the equation of a circle of radius r comes from, but we have this as a tool to play with. And you're like, Dylan, I'm still confused, what the hell are you talking about? Okay. Basically, in order to convert currencies, to go backwards, right, we can only use formulas that we have. So for instance, we have this formula. We could try to use this to help us turn this from polar coordinates back into x and y. The problem is that in that equation there, these guys have a whole bunch of thetas floating around, and this equation right here doesn't have any thetas. So it doesn't really make sense to try and use those equations there. But we also know there's also one more relationship here that I didn't write earlier, which is that x squared plus y squared is equal to r squared. And this is like a permanent identity. Okay, that's going to be super useful for us. And you're like, I still don't see it. Well, this, if we start over in polar land with r equals 3, and then I square both sides of that thing, I get r squared is equal to 9, we can use the identity that x squared plus y squared equals r squared to replace r squared with x squared plus y squared. And then this gives us the 9, and boom, we are back to our Cartesian coordinates that we know and love. So this is a pretty useful transformation to kind of go back and forth. Okay, so for instance, let's do another one. Okay, this is probably a little weird. I will continue doing some for you. So for instance, let's do one from. So for example, let's rewrite the line y equals 3x plus 2 in polar form. Okay, let's do this. So what do? So remember, we're starting over here. We're starting in our x and y land. We are going to we want to end over here in our r and theta land. That's our polar coordinate land. And we're starting over here in x and y land. And we're starting off with the equation y is equal to 3x plus 2. And the only things that we have that are going to get us from, that are going to convert us from Cartesian to polar is x is equal to r cosine theta, y is equal to r sine theta, and x squared plus y squared is equal to r squared. Those are the only tools that we really have. But lucky for us, this is actually pretty simple to do. We're just going to kind of start our journey, and we're just going to plug in what we have for y and what we have for x. So I'm going to get r sine theta is equal to 3 times r cosine theta plus 2. And the way that it's usually written in polar coordinates, equations are usually written in the form r equals something in terms of theta. So even though we have actually, we've accomplished our goal right here. Technically, r sine theta equals 3 times r cosine theta plus 2 is writing it in polar coordinates like that. That is the equation of this line in polar coordinates. It's kind of equivalent to if you wrote the equation xy equals 2x minus 6 and you said this is our Cartesian coordinate. Normally our goal is to like set it as y equals something because that's how we're used to seeing it. So for polar coordinates, we are going to do the same. And so all I'm going to do is a little bit of algebra. I'm going to try putting everything with an r on one side. So we have r sine theta minus 3r cosine theta is equal to 2. And I'm just going to factor out an r from everything. So I have an r times sine theta minus 3 cosine theta is equal to 2. And now my last step is to divide everything by the sine theta minus 3 cosine theta. And I'm going to get 2 divided by sine theta minus 3 cosine theta. Okay. Right. This right here is our equation in polar form. Now, a natural question you may have is, who cares, right? Who cares? And largely, I'm actually going to agree with you here. We don't, I really don't care that you can do this or not. The purpose of this is to notice that this equation looks terrible, right? This equation looks terrible because we used polar coordinates on something that is a straight line, okay? We used this on a straight line. And so the equation in polar coordinate land looks absolutely god-awful, looks bonkers, bananas terrible. But you'll notice that when we used polar coordinates on a shape that was naturally round, like a circle, we get a really, really nice, succinct, pretty neat formula to work with. R equals 3, boom, circles, stuff like that. Okay, and so that's going to be kind of something that in the future, as you progress in your math courses, you're going to notice that you usually want to use polar coordinates to do math over here. Because since you can kind of think of this as a currency exchange, if you can do the same math over here on this really nice equation, then when all you need to do is kind of convert it back and you kind of get your answer. Whereas working with x squared plus y squared equals 9 can be kind of a pain in the butt. But if you were to work with something like this, maybe working with y equals 3x plus 2 is smarter, and you wouldn't want to put it in polar coordinates because in polar coordinates you get something super nasty and it's not going to work very nicely. Okay, so this is kind of how you go back and forth between them. Maybe I'll do one more where we go from polar to back. So for example, let's see, convert r is equal to 2 secant of theta to Cartesian form. Okay, and then maybe we'll sketch the graph. All right. So again, we have to remember that we're starting in polar form. This is a polar equation. And the only transformations we have to work with to get back is x is equal to r cosine theta, y is equal to r sine theta, and r squared is equal to x squared plus y squared. Maybe I'll write it the other way. X squared plus y squared is equal to r squared. And so your goal is to play Sherlock Holmes with this thing. There's no like, oh, this is the best way to approach this. You're going to play Sherlock Holmes with this and try to see if you can finesse it back into something that is in terms of just x's and y's. So there's a couple ways I might try going about this. So my first thing that I might look at is like, all right, secant of theta. We don't have anything here in terms of secant. But what I do know is I have things in terms of cosine. So why don't I write this as 2 divided by cosine of theta? Now, you might be like, all right, this didn't really help. Sure, but now I could multiply both sides by cosine theta. I can multiply that side by cosine theta and this side by cosine theta. And all of a sudden, I get r cosine theta is equal to 2. And r cosine theta is very famous for being x. So this is just the equation x equals 2, which is a vertical line, right? It's a vertical line, goes straight up and down, just like so. Okay, that might be one way of doing it. Let's try something else, completely different, totally bonkers. Let's just see if anything else works. So what else might I try? Maybe I didn't recognize the secant, and I was just, maybe I'm focused on the fact that I know r squared is equal to x squared plus y squared. So maybe I try multiplying both sides by r. Because if I do that, I get r squared is equal to 2r secant theta. And then, let's see, this side becomes x squared plus y squared. And the right side is 2r secant theta. I think we're still going to get stuck here because even though we've successfully turned the left side into x squared plus y squared, in doing that, we had to multiply the right side by an r. And even if I turn the right side into 2r divided by cosine theta, right, we're still kind of toast right now because, well, let's see. If I do this, maybe I can finesse this equation a little bit. And I can use the fact that I could rewrite this as x divided by r is equal to cosine of theta. And I can replace that right here. And you might be wondering, Dylan, why are you doing this? Well, because if I do that, I get x squared plus y squared is equal to 2r divided by x over r. And let's see what happens here if I go about doing it this way. So with the division, the left side is still x squared plus y squared, and the right side becomes 2r squared divided by x, and r squared on the right side, r squared is the same thing as x squared plus y squared. So we have 2 times x squared plus y squared divided by x, and since both sides of this equation have an x squared plus y squared, I can cancel them out. And so this leaves us with 1 is equal to 2 divided by x. I can multiply both sides by x, and I still get to x equals 2. So as long as you don't quit, and you kind of keep going, and you just keep messing around with things, and you just try and tackle little tiny bits at a time. The first thing I tackled with this case was r, then I tried tackling with the secant of theta. And as long as you keep going, you're always going to be able to undo the equation. It's just kind of a matter of persistence. Yes, some ways are easier. Yes, some ways are harder. Okay, so that's polar coordinates. We've kind of seen the usefulness of it. And so the last thing that we're going to do is to just talk about how to sketch some graphs of polar graphs. Okay, so if we want to sketch a polar graph, I have 2 recommendations. I would recommend doing this by hand and simply making a table. So for instance, if we were to graph, say, r is equal to cosine of theta, right? I want us to sketch this graph. What I'm going to do is I'm going to first make a polar graph. So just very loosely kind of draw a couple. So this is a circle radius 1, This is a circle of radius 2, circle of radius 3, right? So on and so forth. All right, cool. So if we do r is equal to cosine theta, just like with any other graph that I would try to sketch, if I had no idea what this looked like, I would probably put, say, like my theta here, my r here, and just get some values. So for instance, I might try theta is equal to 0. And I know cosine of 0 is 1, so my radius is 1. So I know that I'm going to have the point where theta is 0 and my radius is 1. So that's this point right here. Okay, r is 1 and my angle is 0. Fabulous. Then let's see. Let's do, what if theta is equal to, let's do pi over 3. I'm picking pi over 3 because I know cosine of pi over 3 is just 1/2. So pi over 3 is 1/2, so that means roughly at the angle pi over 3, I'm only going half the distance, so maybe about halfway, so maybe like here. And that right there is the point 1/2 comma pi over 3. Okay, what about at pi over 2? Pi over 2. Cosine of pi over 2 is 0, so we're just kind of sitting at the center. So if I'm trying to graph what this looks like already, just trying to like fill in some dots here, it kind of looks something like this. So let's do the other side of it. What if I do, let's see, what if I do, so we did pi over 2. What if we do 2 pi over 3? So 2 pi over 3 cosine is negative 1/2. So at 2 pi over 3, so 2 pi over 3 would typically be here, but because we're at a radius of negative 1/2, we're going to be going the opposite direction. So we're going to end up right there. So that is the point negative 1/2 comma 2 pi over 3. And starting to, you know, finish this graph a bit, we get there. And what if we're at, say, let's do pi. What if we get to pi? Well, cosine of pi is negative 1. And then we should just have this and the same issue. So normally pi would be in this direction, but because we have a radius of negative 1, we're going to be in the other direction. So we'll be back kind of at the start. And so it looks like what we get is the perfect equation of a circle that is not centered at the origin. It's centered at 1/2 comma 0. Okay. And so that's what this equation is. That's what this is. This nice, super clean equation, if I were to put this in Cartesian coordinates, would look like x minus 1/2 squared plus y squared is equal to 1. That's a circle of radius 1 shifted to the right, which is a lot more heinous than this just r equals cosine theta. How would I turn that into this equation? So if I was asked to turn this into Cartesian, I would probably multiply both sides by r, because if I do that, I get r squared is equal to r cosine theta. And I know that r squared is x squared plus y squared. And I know that r cosine theta is equal to x. And this, if I shift some things around, I get x squared minus x plus y squared is equal to 0. You might be like, that's ridiculous. But if you use completing the square on this and you take a trip back to Algebra 2, completing the square will say all I need to do is I need to subtract 1/2 here, subtract 1 and add 1 to the other side. Oh, no, wait. Sorry, let me think. If I'm doing complete square, minus 1/2 plus 1/4. So I'm going to add 1 to both sides. Add 1 here, add 1 here. And this left side right here is going to turn into x minus 1/2 squared plus y squared, and I'm going to get my 1 on the right. Oh, excuse me, not 1, 1/2, 1/2, 1/2. I goofed earlier and nobody said anything. Of course, nobody said anything. You guys aren't even here. This is a circle not of radius 1. What radius is this, everybody? This is a circle of radius 1/2. And that looks a lot better. 1/2 plus 1/2. That makes a lot of sense. All right, cool. Fabulous. So that should give me this. Wonderful. Okay. Awesome. Oh, no. Great. So that's sketching a polar graph. Sorry for the small little hiccup, but that is how I would graph any polar graph that you were given to graph. We're not going to spend too much time worrying about graphing these things. There's going to be a couple problems that say, hey, play around with this. You can get some weird shapes. For instance, if you get, r is equal to like 2 plus 3 cosine theta, you're going to get a shape that kind of actually looks like this. It's called a cardioid shape. It looks something like that. And the only way you're going to know is to simply make a table and just pick some nice trig values that you already know and kind of plop them in. Okay, so that's polar coordinates. It's just introducing you to this kind of system where we find that sometimes sketching circular or round shapes ends up being a lot nicer. We can take some funky looking circular shapes and turn them into some really nice equations to work with, which is going to be massive in your next couple of calculus courses. So hopefully that was kind of interesting and that we didn't get too far off rails. This is the only video for this week, and the rest of this is just going to be homework and reading some notes. So hopefully that's not too bad. Email me with questions, and I'll catch you guys in the next one.